Hi everyone, in this video we will be performing stoichiometric calculations from balanced chemical equations and identifying the limiting reactant and thereby calculating the theoretical yield and percent yield of a reaction. Okay, so for starters, there are really those reactions that has to stop because of the lack of um, starting materials. Okay, so one of the starting materials got used up and they won't be able to fulfill the what is required in the chemical equation anymore. So let's say for example here I have 10 molecules of H2 and 7 molecules of oxygen gas. Now the H2 here is represented by the white circles while the O2 is represented by the red ones. Alright, so if I have this combination and we know very well that two molecules of H2 will react with one molecule of O2 to form two molecules of H2O, so they react in this manner, then if we have this number of H2 and O2 molecules, we end up with only 10 H2O molecules with an excess of 2 O2 molecules, okay, 2 oxygen gas. So what happens there is one of the reactants must have gotten used up, okay, such that there are left over, and we know that substance or we know that molecule to be H2, okay, because there are leftover O2 molecules. So there is a term for that particular substance or reactant that got completely consumed in the reaction, so we call it a limiting reactant. All right, so this is the first reactant that is consumed in a chemical reaction, and it will affect the product yields. Okay, it will affect the uh, amount of products that will be formed. All right. So there are also a few terms I'd like to point out. So if you have theoretical yield, that is the yield of product calculated based on the stoichiometry of the balance equation and the amount of limiting reactant. Okay, so after calculating the amount of products based on the limiting reactant, we can obtain the theoretical yield. Now, there's also the actual yield, which is the yield of product actually obtained from the experiment. So there are many processes going on while doing the experiment. While, for example, while transferring solids, some of the powder may have stuck into the container. All right, or there may be some human and gross errors that are associated with in the experiment. So the amount of product actually lessens. All right, or there are some moments when the reaction actually stops even before it is completed, okay, or there are side reactions. So meaning to say you may have calculated a certain expected value as your theoretical yield, but what you get in your experiment is quite different, is usually lesser than your theoretical yield. All right, and we call that a value obtained from the actual process of doing your actual yield. So that's why there's a need for us to report the percent yield of a reaction, which is basically the actual yield divided by the theoretical yield times 100, okay? So that we can report it in percent. So actual yield over theoretical yield times 100. So the goal for every experiment is to make the percent yield as close to 100 as possible, but that is very very difficult to attain. Okay, that's why people have to keep upgrading their equipment. They have to keep revising and revisiting their methods so that the percent yield will be greater. All right, so here is an example of a problem that involves limiting reactants, theoretical yields, and percent yields. Okay, so in here we are given a fuel mixture used in the early days of rocketry consisted of two liquids, namely hydrazine, that's dinitrogen tetrahydride, okay, and 2H4 with a molar mass of 32.05 grams per mole, and dinitrogen tetroxide, which is N2O4 with a molar mass of 92.01 grams per mole. They ignite on contact to form nitrogen gas N2 and water vapor H2O. and you are given the molar masses also there. Now, limiting reactant problems are actually a stepwise process, and they can be completed until we reach the percent yield. So in this kind of questions, you might be asked what the limiting reactant is, what the excess reactant is, and how many grams of the product of a certain product will be produced. And you will also be asked, given an actual reaction yield, then what the percent yield is. You may be asked what the percent yield is. All right. So let's start. So the first thing that we need to do is to form, okay, or formulate our chemical equation. Right. So let's have drawing here. So let us now form our equation. So it was said that nitrogen, let's zoom out a little bit so that you can see the steps. All right. So you have N2H4 gas. Okay, I'll not write the subscripts anymore. Plus N2O4 will give you nitrogen gas, N2, and H2O. All right. So what could be a balance equation here? So first, we must take note that the number of atoms on both reactants and product side are the same. So here is the balance equation. We place 2 before hydrazine, and then 3 before N2. All right. That's 3 before N2, and we also have to place 4 before H2O. Alright? So now that we are given the balanced chemical equation, it's good if we can also write down the given values. So for N2H4, you are given 1.0 times 10 to the 2. Okay, this is basically 100, but it's reported in 3 SFs. Okay, times 10 to the 2 grams of hydrazine. Now, for nitrogen tetroxide, dinitrogen tetroxide, you are given 200, or that's 2.00 times 10 to the power of 2, then grams. Alright? So how is this different from your previous stoichiometric problems? You might have noticed that the amount of reactants are given for both. Okay, so you have two values for the reactant. So that will be your clue right away that this is a limiting reactant problem. Okay, and then you might be asked for the theoretical yield, percent, and the percent yield. All right. So how do we determine the limiting reactant? So the first thing that you have to do is to try to look at your problem. Okay, take a wholesome look at the problem, and then you have to choose which among the products will you calculate for. All right. So this is very important so that you will not be doing a lot of calculations. So in here, since eventually I will know that eventually I will be calculating the amount of nitrogen gas, the mass of nitrogen gas, then we might as well use our N2 as our selected product. All right, the nitrogen gas. And then how do we find the limiting reactant? So first step is for us to calculate here the amount of product that will be formed by a given reactant A. Alright, so now that we have chosen N2, because it's eventually in the problem, we will be solving for it, we have to calculate how many grams of N2 will be resulting from N2H4 and from N2O4. Alright, so we use both uh, reactants. So let's just do step 1 here. The number of grams of N2 or nitrogen gas. Then let us specify from which reactant this is. So this is from N2H4. Alright? Is equal to we use the given for hydrazine N2H4. We know that this is 1.0 times 10 to the second grams of N2H4. Alright? And we convert it, okay? We convert it into the number of moles by using its molar mass as our conversion factor. Now, in the problem, the molar mass is already given. That's 32.05 here, grams per mole. So we have to cancel out grams of N2H4. So we are practically dividing it with the molar mass. So 1 mole N2H4, and we know that is 32.05. Now we can cancel grams of N2H4. We can cancel grams of N2H4. What we can do next is to convert moles of N2H4 into moles of nitrogen gas. Alright? So what we needed was to have moles of N2 on top and moles of N2H4. Right? So this next conversion factor is practically your mole ratio. Okay, the mole ratio between N2H4 and N2, and we can get the mole ratio from the balanced chemical equation. All right, so N2 here, it says in the balanced equation that 3 moles of nitrogen gas will be produced from the reaction of 2 moles of N2H4. Now we can cancel N2H4 here, and we can also cancel N2H4. Then after that one, we need to convert it into grams of N2, right? So again, we use the molar mass of nitrogen gas so that we will be able to cancel moles of N2, okay, and end up with the unit of grams. So for nitrogen gas, it is 28.02. Alright, now we have to cancel, we get to cancel. So now that we ended up with grams of N2 as our unit, we may carry on with our calculation. So for those who are still having confusion with their scientific notation, in the calculator, you input them as 1.00 exponent, EXP, or the button beside the answer button. It could be EXP or times 10 to the x, right? So if you can see that notation. So that is 1.00 exp2 divided by 32.05, and then times 3 divided by 2 times 28.02. Alright? So you have an answer of 131.13. This is grams of N2. Alright, so since the given is in 3 significant figures, we may end up with 131 grams of N2. Now hold this yet, because we still have to calculate the amount or the grams of N2 from the other reactant, which is basically our next step. Okay, so we repeat the calculation for reactant B. So in here, we will be having number of grams of N2. So this time from dinitrogen tetroxide already, N2O4. Alright, and we know that it is 2.00 times 10 to the second grams of N2O4, and then we multiply it with the molar mass. Yeah, we're still performing stoichiometric calculations. So in the problem, the mass of N2O4 was already given, and that is 92.01 grams per mole. So we divide it, are given with the molar mass. This is 92.01, and then grams N2O4 And then this is 1 mole of N2O4. Then we can cancel grams, we can cancel out grams of N2O4. The same process, we use the mole ratio so that we can get the moles N2 and cancel out moles N2O4. Alright? So our goal is to cancel this numerator with this. Alright? So, but on the balance equation, we can see that for every 3 moles of N2, only 1 mole, okay, it's not reflected here in the balance equation that there's a number, so we assume right away that it's 1. So we get to cancel N2O4. And then after that one, we can use the molar mass of N2 of nitrogen gas so that we can end up with the total mass of N2. Alright, so this is 28.02 grams of N2 is to 1 mole of N2. Now we can cancel moles N2, we can cancel moles N2. Alright, now we can carry out the operation. This is a 2.00 exponent 2 divided by 92.01 and then times 3 times 28.02. Alright, and so we have 182.7 grams N2, but since we are given up to 3 significant figures, then we may stop at the ones place. This 183 grams of N2. Alright, so this is the amount of grams that we get of N2 from, okay, we go back to our labels, from N2O4. And this is from N2H4, from hydrazine. Alright? So just base it on what you've written as your ask. So therefore, what do we do to make sense out of this information? You notice that there is lesser amount of nitrogen gas in N2H4. So in choosing the limiting reactant, we have to choose the one that gave us the smaller amount of product. And in this case, it is N2H4. Therefore, in here, our limiting reactant is N2H4. So let me label our limiting reactant as LR. So it's hydrazine N2H4, while our excess reactant, so we expect that there is an excess of N2O4. And this is our answer practically for letter A. Alright? So again, the limiting reactant is the one that gave us the smaller amount of product. Alright? That means it is used up earlier in the reaction than the other one. And in terms of how many grams of nitrogen will be produced, this question practically asks for our theoretical yield. Alright? So how many grams are we expecting to be produced for nitrogen? So in this case, we base the theoretical yield on the amount of product that has been generated from the limiting reactant. So as for this case, our theoretical yield is 131 grams of N2. Alright? 131 grams of N2. And this is our answer for letter B. Alright? And then we are also asked if the given reaction happened, so this is a stem or this is a continuation of this stem in boldface, and the actual reaction yielded 126 grams of N2. What is the percent yield of N2? So 126 grams of N2 I hope you know what quantity it is based on the clues. So this is the actual yield of the reaction. So this is A, our A, Y. So in getting the actual yield, so this is now letters, or in getting the percent yield rather, here, let me spell it out. It's basically the actual yield, AY, over the theoretical yield, and times 100. Alright? So if your actual yield is given, and in the problem it was stated that it's 126 grams, so there's a 1 here, right? 126 grams of N2. We just divide it with our theoretical yield, which is 131 grams. Okay? Notice that the theoretical yield is almost always bigger, okay, than the actual yield, because that is what you expect. That is what you have calculated stoichiometrically, while the actual yield is what is obtained in the experiment. And as explained a while ago, we get the actual yield. There is a certain measurement for the actual yield because of a lot of factors, like losing some particles of the product in transporting, or there can be side reactions, right? So we'll multiply this by 100, and then we carry out the operation. Notice how we cancel grams here. So this is basically 126 divided by 131 times 100. And then we end up with 96.18, okay, or 96.2% of nitrogen gas. That was our percent yield, right? So we have the following answers to that problem. Our limiting reactant is N2H4 or hydrazine, and then our excess reactant is N2O4, and our theoretical yield is 131 grams of N2, and our percent yield is 96.2% of nitrogen gas. So here is the whole solution, and I'd like you to reflect or take time also, okay, to absorb the information. Alright, so I hope that you find this video helpful, and you may now take a break and have a cup of coffee. Here's to having or performing well in chemistry, performing well in stoichiometric calculations. Have a nice day.